All right, let's begin and get into the video and the stream. Thank you for checking us out. To the Twitch viewers, sorry that I didn't stream on Wednesday, but it was New Year's Eve. It completely slipped my mind, and I spent time with my wife and our cats doing New Year's Eve things and having fun. It was a nice break. If you like what we're doing on this channel, if you're really enjoying the video so far, definitely like and subscribe. Hit that bell notification to be notified of future videos. And I know this is crazy, but you know what? I'm all about crazy. Let's really mess with the algorithm and see if we can get to 1 million subscribers by the end of 2026. You know, let's just go for broke. Let's just send it. Let's just go. So in the last video, we received the PCBs, and I wasn't sure on when I wanted to build or anything like that. So we'll do that Saturday afternoon, just mainly because it's 6 o'clock now. It's been a busy day. I don't want to push myself too much harder. I want to just kind of get through a nice, smooth stream. We can cover a couple other things, share a couple other things, maybe share a couple other things with you. A couple other files I'm going to throw in on the project resources for you to be able to work with. And then maybe write some more test plans for when we do get the board assembled. We've got the primary test plans already written for the basic testing, which will let us build additional boards. But I want to do a deep test plan for would be considered more destructive testing, such as shorting things out, reversing voltages, trying to apply voltage to outputs, things like that. Things that could potentially damage the board, but things we need to test and validate. So that's where we're going to go. Maybe we'll work on a few other things. I'm not sure. Tonight, it's going to be an hour stream, so we'll see. It might be a little bit all over the board because I'm just as eager to build as you guys are. I'm really eager to see this board actually work. But first things first, there's firmware that we need to develop. So we should get the boards built tomorrow. As far as testing, that might wait till Sunday. When we can start doing some of the testing and shoving some of the firmware into the board and seeing what we can do. But tonight's stream and video, we will look at this other stuff. So I've kind of started another scratch notes and a markdown file in the resources directory. This is just to make it easier for me to organize my thoughts on other things, to keep track of, and to help you guys follow along and understand the logic behind it. Things like some calculations, try to figure out like our power resistors, some other things. So that's what this is, what you're seeing here. So first things first is I've designed for the single button, the test button, just a single little 3D printed plastic enclosure with a lid to enclose the button. And, that way it gives a more solid foundation, protects the wiring, protects the user from any sharp edges and stuff. These holes right here are designed for M3 inserts, for heat set inserts. You get those guys in there, and I used M3 button heads. I used black oxide because I printed this in black 3D black PLA. So I used black oxide button heads. The length, I think 4 millimeter were fine. But I think I've got it set so you can use up to 10 millimeter screws. But 4 or 6 millimeter more than enough to hold this little lid on, because it insets in here and it fits pretty tight. This hole might be kind of snug for some of those buttons. Let me show you. I'm not as prepared as I thought I would be. I'm talking about, I'll just show you this just to give you an idea of what I'm talking about, because you can find this kind of stuff on Amazon. These are latching, but you can use whatever. So basically for these guys, they're you typically see these in automation equipment. So these are latching styles. You push on, they lock on, they lock off. They have single pole, double throw, normal open, normal closed, and they have 24-volt illumination LEDs built into them, and it comes in 5 different colors. There are 5 different colors in that box in the pack. The one I'm using is a rectangle version, and it's momentary, so you push it and it doesn't latch. But this is just to show you what I'm talking about, what it's made for this style, the round 16 millimeter. So that's what that button box is made for. The hole here can be rounded out a little bit more with a deburring tool or another tool if you need to, if it's too tight for your button to fit through. But that's what it's for. Maybe I'll get a picture. I'll definitely show an image of the finished product actually together and used, when we actually go to do the bench testing. But yeah, so I've got the STL files for this, along with the Fusion file. It'll be uploaded after tonight's stream in the Git repository. And so you can pull this down, for instance, PLA, but you can print out ABS or whatever material. Again, the lid insets in here. It's got a snug fit, so it is not likely just to fall out, but again, M3 inserts and things like that. So you'll get that. So close Fusion out, and we'll take it sweet old time. So, I just kind of threw a little README in here for the button box with those files, the STL and the Fusion 3D file. So you can open it up if you had Fusion 3D, learn from it, modify it, whatever. It's just something, it only took me like 20 minutes at most to throw together. Printed first, the first print, everything went together just fine. So I just had to open up the buttonhole a little bit more because I purposely make things a little smaller because you got to account for tolerance slop in devices. So I've got my scratch notes here. Also, I also did some digging and found the heat sinks I want to use, and I bought some, and I've got some coming in. So this is the heat sink. It's a little black anodized 8.5 by 8.5 length and width and 8 millimeter tall. It's designed for BGAs, but this is the same size pretty much that ships with the stepper motor breakout, the driver chip breakout boards that I picked up off of Amazon. So they work out perfectly for that. So they'll fit. Unfortunately, these don't have the adhesive tape with them, so I had to order separate. They're pre-die cut pieces of adhesive thermal tape for these heat sinks. So I've got them coming in too. I've got 10 of each, which should get us through what we need. Again, I could buy like a whole kit of these things off Amazon, but I'm shooting for repeatability and reliability, and no-name companies off of Amazon that I'm just going to use the term fly-by-night, that just are money grabs and just there to make, a quick buck. You can't build a business on. You don't want to rely on those type of suppliers. You want to be able to have a reliable supplier that you can find alternatives for and get any documentation certifications with them. So that's why I'll pay the extra money to get reliability. That's more important in developing a business than saving money up front. Yes, you need to save money. I get that. You can cut corners here and there in development, but at the end of the day, when you're putting a product on the market, that will always come back to bite you. Because what can happen is one of these fly-by-night suppliers that you find on Amazon, because since Amazon doesn't sell everything themselves, because even I've got a seller's account on Amazon, I've got one thing listed for another product. They could just close up shop and you can never order from them again. And a lot of those companies do that. They start getting bad ratings. What they'll do is they'll just close up shop, start up under a new weird name, same products, same stuff. But now you have to find that new supplier and vet them. And then you're back at square one with your ISO, with your QMS processes. Not a reliable way, not a smart way to run a business. Yeah, it saves you money now, but it can cause you headaches and a nightmare later. So I went ahead and updated the bill of materials. The spreadsheet for that. Updated the bill of materials, calling that part out. Then I updated, let me close that out. I know we're a little bit helter-skelter, but, I just want to catch you up to things I did off camera because, some of this stuff is kind of just boring work. Updated the budget to show the new expenses, buying those materials. And then inventory here, products. And since that's technically assembly level, which helped us out a lot, I got Odo updated for the assembly level PCB, got into the bill of materials, and updated it with the heat sinks and the thermal tape, which in turn updated the manufacturing. SMT, that's SMT, this is PCB level. No, wait here, this is, yeah. So that we haven't made yet. And then now, because we're waiting on those to come in, it's saying we're behind, and that's fine. I can lie to the system and put one of each in and use one of the extra heat sinks I had from another project if we really needed it. But I'm not too terribly worried about this. For the initial pass through of testing, I probably will lie to it and add one of each quantity to my existing stock, just so I could be able to close out this work order, and we can run through that process down the road, or maybe worry about it later, and I can run you through that that process of closing out that work order. We'll figure it out. I'll get an action plan on that. But we still have to get the fan assembly built up. Maybe we'll do that over the weekend too, because I was also working on getting my workshop space set up in a way with a camera, testing some camera stuff out. Found another way to interface a camera, so I'm getting my workstation over there set up to be able to use OBS and my wireless mic and everything, so I can switch over to it and we can still do these videos and have pretty much everything we need to actually do them. So that's it for Odo. So again, back to the notes here. Let's see, is there anything else I wanted to cover that we caught up on? Oh, that's enough. So back to the documentation. So we want to work on these things, these performance requirements. PCB temperature rise, motor current output. So we'll need to set everything up. So according to the data sheet for the regulators, which I probably should have left that open, but that's fine, because the data sheet was designed and their testing was done with a 1 amp load current. I better load up that bomb and pull up that data sheet again, because we want to make sure we match their, let's see here, that is, see, these are all the same, technically. The 203 and the 205 are the same. Let's see if we can, okay, yeah. Okay, yeah. So their ripple was measured actually at the full current output of 2 amps. So what we need to do is basically go ahead and select the ripple voltage on 3.3 volt supply at 2 amps loaded. And it's going to be the same thing for the 5 volt. So again, that's why I'm just doing this as like a scratch pad to stay consistent, and you'll have access to it. It's going to be part of the file upload, just so you can help follow along with the logic of what we're trying to do. So their ripple they call 20 millivolts per division. There's like hardly anything there. Wow. Well, their ripple, see if I can actually see it written, but based off of that, we're not even at peak to peak. That is 20 millivolts right there. So let me pull you what I'm looking at here. So right here's what I'm looking at. Output ripple at 2 amps load. So ripple is just your AC noise that's induced onto a line either by an adjacent circuit that could be noisy, a motor, or in this case, the ripple would be caused by because it's a switching voltage regulator. So it's switching on and off several times. You know, I think it's in the megahertz range. Let me see what. Yeah, the switching frequency is 1.1 megahertz. So it's going to induce some kind of noise in the output. Your bulk capacitors on the output side is supposed to help smooth that out, but it's not always going to smooth it out. High frequency noise is sometimes really hard to get rid of. But that's what causes your ripple. Multiple different sources for voltage ripple, but that is one of them, the high frequency switching. So 20 millivolts basically right here. And that guy is not even a half of that, half that magnitude. So we're talking peak to peak voltage ripple, maybe 5 milliamps, if that, or millivolts. That is insane. That is some really tight ripple regulation. Because too much voltage ripple and a DC component could mistake it for a signal, or some older components, if they weren't protected right, could see that ripple as a voltage spike or a brownout as it dips down. Voltage ripple typically causes undesired performance in electronic components, especially the older stuff. The newer stuff, they're better designed, better protected to handle ripple, but ripple's bad. You want as little ripple as possible. Okay. So that's under load of 2 amps. So what we need to figure out, 2 amps loaded. So Ohm's law. To 2 amps and the So this is what we need to do. So we need to determine the resistance needed to get the power supply to source that 2 amps. So we have to force it without anything to actually coax that power supply to say, hey, I'm loading you down for 2 amps. It's not going to draw. It's just going to sit there and just basically not draw anything, not deliver anything. And then we need to make sure the resistor can survive dissipating that much heat. So that voltage drop, the 2 amp draw, is going to cause that resistive unit to basically heat up. So imagine an element in a toaster. That's how it works. So your toaster toasts your bread by using a resistive heating element. And that resistive heating element, due to the nature of a resistive wire or device, basically causes the electrons flowing through it to grind against the internals. Let's just say that. And that grind, as it goes through, causes friction, which causes the device to heat up, causes the wire to heat up. And then, so in your toaster, you can see it glowing. That red glow is basically infrared energy, the heat energy, just radiating visible light. It's that hot. And that wire is designed for it. I think it's, I can't remember the type of metal that is used in those type of resistive heating elements, but it's designed to handle that temperature. But, you know, if you're looking at like a 1/4 watt resistor, one of the little typical resistors or surface mount resistor, it's not going to handle 2 amps. It's not going to push. It's not going to handle the heat going through it. It might be able to handle the current, but not the heat's going to be generated. So basically that's what we're looking at. Now a resistor, if it gets too high in value and causes too much of a grind, it doesn't let enough current flow. So the whole theory is the whole idea of resistance is you want to cause enough of a grind that you're gonna, you want that like almost like a short circuit. Well, you want to cause a short circuit, but you want to kind of grind it, to slow it down. But that grinding causes that heat. So we need to source 2 amps, so we're at 3.3 volts. So using Ohm's law, so our resistor, the unknown variable, equals V divided by I, your voltage divided by your current. So equals 3.3 divided by 2. And so, 3.3 divided by 2. So R should be idealistically 1.65. 2, 3, 4. 1.65 ohms. So it's almost a dead short, but it's just enough resistance to basically limit it at 2 amps. Because a dead short would cause it to completely short out. It would cause the power supply to fail. Because it would be trying to deliver unlimited current. So we need to impede it to slow it down just enough so it only delivers 2 amps. So 1.65 ohms. Now, we need to figure out if we can find a wire around a heat resistor to do that. But first we need to kind of figure out what kind of temperature. So that's where power comes into effect. Power is basically the energy dissipated, which technically gets converted into heat. So it's P equals V times I. So P equals 3.3 times. Let's get rid of that X, because that can be confusing. Let's use the asterisk. X2. P equals 6.6 watts. Now, 6.6 watts doesn't seem like a lot, because this is a small number. But converted into like audio energy, that would be pretty loud. A 6-watt speaker is actually pretty loud. Could actually damage your eardrums with the decibels it could push out. Especially if it's too close to your ear. So, if you have your headphones trying to push 6 watts, your chances are you're hurting yourself. And in resistor terms, just say no 603 resistors only 100 milliwatts. So 0603 standard 0603 resistor and 0603 resistor handle a max of milliwatts or 0.1 watts. So at 6.6 watts, you are toasting that little resistor. That thing is going to be smoke. That thing is going to catch on fire. I mean, if it doesn't burn out in open circuit first. That's just to put it in a perspective. So we need to make sure we can source a 1.65 ohm resistor that can handle 6.6 watts. So, the problem is, I'm kind of like looking. So there's a kit on here that are, see, that's only 5 watt. Even these resistors won't be able to handle that. So let's see here. Power resistor kit. What we might want to do is look for a variable wire wound resistor. See now here, oh, this might actually work. A little bit pricey, but But for a test rig, and we could dial this in. Oh, might be able to get really close with this. This could do 50 ohms. Okay. So I'm just going to drag this over the screen and show you what I'm looking at. So I might have to work on ordering one of these. So this little guy, basically a wire wound high power potentiometer, handle up to 25 watts. So we can basically control the output current or output resistance. So we have this little guy, which not bad for what it is. I may order one of them. And there's also its bigger brother that can handle 200 watts at 10 ohms max resistance. So I don't know if we need anything that high value right this minute, because 25 watts is not that bad at all. So we'll kind of keep these options on the table right now, but I might pick up one of these and kind of... So what I might try to do is, if I, what I will do, not try to do, what I will do, is I will kind of throw in a bill of materials for test fixturing and things like that, and kind of track this off the project budget, because technically that's what you would do, is since this would be it's initially bought for this project to do test fixturing, you would take that into account in your project budget. This is the kind of stuff you have that budget for. I may end up having to get this guy too because of the 200 watts. I'll keep looking to see what else is available. But this guy right now so far is the tastiest, because it can go up to 50 ohms and 25 watts. So that meets the minimum spec. Let me drag this guy off. So that meets this, and we should be able to dial in the resistance pretty close. It's not going to be perfect, but, you know, we'll have to factor in our tolerance values. And there we go. Factor in tolerance of test resistor. So it's going to be plus or minus equals plus minus. Let's start with 20%. So let's just kind of start there with our tolerance values. So 6.6 watts, it definitely will satisfy that. Now let's go to here. So before we can even completely write the test, we definitely need to figure out what we want to buy and design for the test. I've got some project boxes I might be able to set up and use to definitely set some stuff up to help keep it cool. So this is going to take some additional time to get everything set up, but that's the name of the game. With the streams and stuff, we'll try to I'll either bring you along for the ride as we go and devise these test fixtures, who knows, as we build them and kind of lay them out, show you the, be part of the process. That's what we're going to do, because that's kind of what this video series is. I don't want to do everything off camera, but some of it I just decided to go and nail out, like figuring out the heat sink and all that. But I figured maybe going through and building up a test fixture and all this for this would probably be kind of fun and exciting. So we know our, V over I. So we know our resistance needs to be equal to 5 volts divided by 2 amps. So it's going to be even a lower. What's really going to get us is the 2.5 ohms. So let's copy this. So now we got to figure this out. Okay, So we're at 10 watts of dissipative power. So the cool thing is that one, the smaller guy can handle up to 25 watts. So we're still under half of the amount of power it can handle. And we're going to put a fan in the test fixture holding it together. I might have to look for a metal enclosure and drill holes and get everything all set up, but we'll do what we got to do. We can always use the 3D printer to print out templates, drilling templates and stuff, and go from there. I've done it before. It's an excellent use for a 3D printer, is to make thin, 1 millimeter thick drill templates for things. And then you can just kind of tape them down or whatever and make your drill, draw your drilling and stuff. So the 3D printer is really great for things like that. Like, say you want to drill mounting holes and the airflow holes for something like a fan, 3D printed template, and just tape it down really good, and just drill your mounting holes and you drill your airflow holes, and boom, problem solved. Works really well. So so far that wire wound resistor looks like it'll hold this guy too. Now we're going to do 2.5 amps on the stepper. So this is where it's going to get crazy. So R equals V over I divided by 2.5. So the resistance is going to be pretty decent. So we need 9.6 ohms. All right. We're going to do this just to make sure it's all spelled out. Here's where we're going to really I'm going to have to really consider what we're going to do for this guy. 24 times 2.5. This is what's going to just destroy it. 60. So I need a load that can handle 9.6 ohms, 60 watts. And the funny thing is that big pancake looking fella, I mean, I don't know what, will definitely handle it. Maxes out at 10 ohms, but it's 200 watts. So we may end up having to build 2 separate test fixtures. It'd be nice if I can find something that can handle this much wattage at maybe a higher resistance value. So I'll kind of keep digging around. And when I settle on something, we'll be able to go from there. But we might have to get this big chunker right here for that guy. As well as the other one. But we'll see. Like I said, I'll keep digging around and see what I can find. If I can find something with a better resistance range, maybe we'll go that way. So that's just to get the stepper motor. So this will also test not only the ripple voltage, but also help test the power supplies, these power supplies right here, to make sure they can source the 2 amps as their specifications say without anything smoking. Again, that's why I consider this destructive tests. You learn a lot about your design, your layout with these kind of tests. So we're going to have to design, like I said, the tests for this. I have to figure out what I can set the bombs and everything. Oh, thank you. Thank you for stopping my print. Let's try you again sometimes. Sorry about the interruption. I'm printing something and my printer decides to have a fit. Sometimes it just doesn't load the filament right. I'll have to check that later after the stream if it doesn't start back up. So that is the bomb taken care of. Let's close that. So that is these guys. PCB temperature rise. So that we might want to do 2 separate tests on this. because we might want to look at unloaded versus loaded, because they will have different performance. So, you know, I would assume that this is there goes my phone with the Bamboo app letting me know that it was having problems. I should have put my phone to do not disturb. Sorry about that. So we're gonna assume maybe just one test above ambient during operation. Let's clarify that. And deep test plan, do I have that in here? No. No. So that'll be the yeah, we'll have to figure all that because that's going to be all that. That's going to be that test rig because we're also have to put the ammeter in there. So yeah, a test fixture would probably be the best bet for this. Who knows? Maybe we can pick up a pre-wired ammeter and throw it in there. Make it just like another little sub project. We'll figure it all out. Either way, it's going to be an absolute blast and it's going to be fun. But things we have to do. Okay, PCB test outright, separate remote test rig, blah, 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 blah. Okay. So we may not need that. Yeah, maybe that's what we can do. Maybe that's what I'll do is because normal loaded conditions where you're not, you know, extreme loading everything down. So yeah, we'll have that test rig that we've got to take care of. So we'll kind of finish this off. Add more here. Blah, blah, blah. R-003. So going back to this. All right. 3.3 volt regulator ripple. Okay. Here. PR3. So with the supply output disabled, because up here we're gonna the PCB assembly. All right. So with it still disabled. So what we're going to have to do is connect the 3 volt test unit black yeah, to TP. I don't know if these test points can handle that much current, but we'll figure it out. We'll figure it out. Great. I don't have the board open. Schematic editor. That is power supplies. So all these different applications have different ways of scrolling and moving. Fusion has one way of scrolling and moving and rotating, and KiCad is another way. Altium is another way. So I'm trying to remember. It keeps getting confused every time I jump back and forth. Okay, it's still upset. All right, I will worry about that later. Filament probably jumped off the spool. All right, it'll be fine. All is fine. Thanks, Steam, for showing my notifications too. Okay, so that would be TP3. TP3. The positive lead to TP. So for this test unit, we're going to have to kind of change it. We're going to have to kind of make something because we want to be able to clip oscilloscope probes to it. An oscilloscope probe to the positive and the negative. 3.3 TP1. TP1. 3 volt. Connect the oscilloscope probe probe to the volt connection and the probe the test unit. Okay, set the to we're going to try to mimic their settings. Just find what window we're on. 20 millivolts per division. 20 millivolts. Millivolts. And that it is for figured for a 1x probe and DC coupling. All right. Now, I'm going to update this while my mind is on it. Ensure that proper PPE is worn. And you know what? Actually, let's get that out of here. Proper personal protective equipment like safety glasses, gloves, whatever. But for this, it would be safety glasses. And I'm going to stress that, and I will continue to stress that even when we go to test. When some of this stuff pops, it pops gloriously, and it can send shrapnel, especially electrolytic capacitors. I don't care if they've got the vent scores in the tops of them. These little boogers will still explode and fly across the room and send shrapnel. They are essentially little bullets waiting to take an eye out. And I'm not joking with you. It's all fun and games, so you lose an eye. I've known people who were hurt by equipment, by exploding and damaging, by electronics failing. I've seen people get across the high voltage side of a television circuit. It's not fun. It's not pleasant. So I will stress that now. Proper protective equipment. Safety glasses, safety goggles, whatever. You can buy this stuff cheap off Amazon. Though I wouldn't trust the cheapest stuff, but it's better than nothing. as long as it lasts to protect your eyes from one flying piece of shrapnel, that's all you need. Then you just buy a new pair or buy a multi-pack, buy a 20-pack of these guys. Paying $1, for a pair of safety glasses is better than going to an ER, going for an ER visit missing an eye. So I will stress that out. Proper PPE. Regular glasses are a good start. Most of these pieces of equipment, when they pop like an electrolytic, you're not talking like the extreme I was making out to be the bullet, but without eye protection, you can lose an eye. At least with regular glasses, you have a chance. The problem is no side shields. That does kind of make for a bad situation, because a lot of things can still come in from the side. That's why you never want to kind of take your focus away from something you're testing. Just like with a dangerous animal or a dangerous situation, never put your back to it. You always pay attention, and you should always be ready to hit the e-stop button or the power off button or whatever. Be ready just to unplug something. So I will always stress that. Proper PPE. Because right here, we're going to be immediately loading the output. Now, granted, we could actually, you know what? What we could do, mind you, is make this more complex and use the same wire wound resistor. Kind of use that setup to do this. All this can be on one test. Okay. So we can have the ammeter in there monitoring the current, as well as, checking, because basically you're going to be bringing up to 2 amps. So there we go. Okay. So we'll have to rewrite this once we get it all done. We'll have to design ourselves a nice little test fixture. Again, I'm sorry I'm so helter-skelter. I'm not using any scripting for this. I've tried sitting down and planning everything out, and that's not how my mind works and solves problems. I just got to be working on it. It's just easier for me to work that way. So this, we're going to just kind of volt loading and we'll test. We're just kind of put that there. We might fix it. And it might be kind of nice to have this on. We'll rewrite all this as we need to. R-004. So this is going to be basically the same thing. We're going to have the power supply unit. We're going to definitely rewrite this for the potentiometers. I will work on getting those ordered. I might just end up ordering both of them. We'll see. I'll see if I can find one that solves all the needs. If not, we'll just get 2. Make 2 separate test fixtures if we have to. We'll figure it out. We'll go from there. So that's the 5-volt loading and ripple test. So we should have our test log. So that's calling for less than 50 millivolts. When their data sheet, I mean, if we hit less than 50 millivolts, then that's good. Because, like I said, per division, so every one of these grids is 20 millivolts. And they're not even, it's barely anything in there. So that is almost too generous for this. But we'll leave it for now. All right. So that should be that performance requirement. Now let's look back up to here to the PRD safety. Reverse polarity, so safety and regulatory requirement. So let's kind of come over here. Safety and regulatory. I'm just kind of drag this off screen real quick. I'm not constantly bouncing back and forth. So SR-001. Test SR-2 IC and SR-003 ISO. Between motor power. There. 825. So I'll just drag this back. So basically the reverse polarity protection test. It's testing that Schottky diode, basically the blocking diode we have at the power input, thermal protection for the driver chip. In a way that kind of get tested here, we could load it. We could load it with the extreme and watch what happens again. We could have a test for that to watch for the fault condition of the IC, because it should fault out if it triggers the motor turn off. Ooh, sorry for that. If you caught that yawn. Holidays just always keep me busy and tired. And then the voltage isolation is basically what we're going to do is put a voltage to the motor outputs and just see what happens. In case this would test a condition in case like something in your cabinet or your enclosure shorted out, or a wire got out of your hands, or heaven forbid a technician installed something wrong. And yes, I've seen it before, and I've seen weirder things. But even though it might take out the IC, but not the rest of the logic circuit, again, I've mentioned it before, you're not really going to be reworking this board and replacing that driver IC. So typically, if one thing smokes on a board like this, the whole board's going to be scrapped. I'm not going to say not to try reworking and replacing that IC, but I haven't. Go back to KiCad real quick, and I'll just show you again. Just anybody new catching on about watching the prior videos, shame on you. But we have, so the ground plane right here. So the top layer, we've got this huge, so it has a big pad by itself, but we put a big old ground pour underneath of it, and that's just on the top layer. Then you've got an internal ground plane, which all these vias tie to, so that, any heat you're applying is going to the ground plane. So the whole board becomes a big heat sink. And then on the underside of the board, I also put a little ground pour, little plane on the very bottom, and tied to as well. So you're sinking heat. You've got one heck of an integrated heat sink system into this board as it sits. So any technique you try to take at pulling this IC off and put it in successfully soldering a new one on, it's going to be a work. And then with some of these resistors and capacitors close like this, you're more likely going to damage cause these pads to lift using hot air to pull it and put a new one down than you are to actually successfully accomplish this task. These pads, even these traces, you'll definitely be melting. These parts will definitely be popping off with the amount of heat you're going to have to sink into this to beat the entropy of the board pulling it all out. So it's going to be a very difficult task. I'm not saying not to try, but this is a very difficult task to do with hot air. So that's why I say sometimes you're better off just unfortunately scrapping the board and starting over, but that's where a good recycling program, waste management program comes into place. And there's an ISO standard for that, 14001, which is all about being environmentally responsible. So that's just to keep that in mind. And that'll apply for this guy. This connector for the fan, kind of not a complete same, but it's got a big copper pore right here, and that ties directly to the ground plane. You'd be hard pressed to rework that, especially because that's the plastic housing. That's going to melt. That's going to basically turn to goo on you. You're not going to really rework that. You're going to pull it off. It's going to be goo. And you'll have to hand solder these tabs back down. Yeah, you can probably get these guys back down. These guys you might be able to touch on, but it's not going to be a nice reliable because you're still going to risk melting the plastic enclosure. Even these capacitors and these power supply circuits would be hard to rework by hand. Not impossible because they are small thermal mass, but things do get difficult when you design a board correctly. It's unfortunate. So you either sacrifice in quality to make it easier to rework, or you sacrifice reworkability to get higher quality out of it. I prefer to sacrifice reworkability to get a higher quality board out of the product, out of the deal. The idea behind this board is it's going to survive. It's going to survive a lot more than what you're going to throw at it. So beefy traces where they should be for the power buses. Beefy ground planes, yeah. So that's the goal, to make it beefy and reliable. So with that in mind, so let's see here. So we've got that. We've got the test plan, kind of the log kind of updated. So we're already kind of approaching the hour mark. And before we get too deep into anything else, we're just going to go ahead and call it here. Because there's still a lot of little things we need to do. I need to, like I said, get some research on those resistors. Maybe get them coming in. That way we can build a test fixture for them. I'll see what else I have, what else I need to do it. And we'll go from there. So this all get pushed over to that. The schematic, I think we're done with for now. I got to dig up some other stuff, my thermocouples and my thermocouple adapters for my meter, so we can set up and write the tests for that. Mainly for PCB temperature rides, because we're going to be using like I said, an IR thermometer, but we're also going to stick a couple of thermocouples to the board and kind of monitor them. We might have to jump between them because I only got 1 meter. Who knows, down the road we might change that. Might design and build something else, another project down the road. All kinds of things. So there's another thing I want to kind of mention is, as part of this project, we're going to kind of add another sub project. And I kind of thought about it because it'll kind of fit in with the end goal of having other test fixtures to test things. So one of the other sub projects that's going to be part of this is a test fixture to test the fan assemblies to make sure that they're built right and they operate properly. That's something you definitely want to do, especially if, at the end of the day, you end up actually turning them to a sellable good that you can sell or, send to customers as replacement assemblies or whatever, however you want to handle it. It'd be a good idea for you to be able to test them. So I was kind of thinking on this, like, yeah, okay, so I could take, from my other projects, and we're going to build it around ESP32. It's going to have a couple buttons on it, LCD interface, just to kind of help you monitor, so you don't have to hook up a serial port or anything to it. I'm going to use an OLED LCD, not a little dinky one, a little bit bigger than the inch size ones. We're going to use a nice OLED display. It's got a very basic text on it, nothing fancy. I found a really light SSD 1306 library for it. For the ESP32, it's really lightweight, and it's not as problematic to deal with as the integrated widget-driven library that the IDF is shipped with. Is a lot easier to configure and work with. I just took the library that I found and made it modular, header and source file for it. So you can just kind of drop it in and just activate it, get everything going with the I2C on that. But I also figured what we'll do is we'll power this from like an external wall wart, like a 12 volt. That way we can also test, be able to test like PWM TAC computer fans. So like if you got like a nice Noctua or something that has the PWM TAC interface, you want to be able to test it, make sure it's working right. If you have questions whether or not your computer's running your fan right, if it's reading right, we could be able to use this test fixture for both. So it'll be something that, will be kind of a project, and I'll be able to sell as an independent unit for that kind of stuff too. So we'll have it to where you can hook just your wires to. I'll see if I can find like some spring-loaded terminals or something that you can easily connect the wires in and out of from the terminals. And then it's going to have the pluggable JST connector for the fan assembly. And then it's going to have the 4-pin connector typically found on computer motherboards that you can just plug one of those computer fans in and boom. Just one fan at a time, though. It's not going to test like 3. I'm just going to test one of them. The 5 volt one for this project. Have the leads for another 5 volt or 12 volt. Maybe we'll figure out how to do it with like a jumper or something, or a switch to switch between 12 volt and 5 volts. And then we'll have the 12 volt for like computer fans, that 4-pin connector. So that's going to be another sub project we'll do for this. Maybe while we're idle, waiting on other things to happen, waiting for other things to happen, or if we want to take a break from working on this, who knows? Things can get hectic and crazy. Sometimes it's nice to step away and maybe do something different. But since it's going to be for testing this fan assembly, I'm just going to go and incorporate it in this project. We'll do it in KiCad. We'll kind of, we'll follow the same process, give it its own project and things like that. And just throw it in here. I figure, why not? Let's just make this journey more interesting and show you guys more of what's really involved in doing a business like this. It's not just about, oh, I've got this project. I threw together my breadboard with an Arduino or, an ESP32, and I think it's great. It's awesome. I want to actually sell it. There's a lot more involved to do it right. Yeah, you could throw it together in KiCad. You can get boards. You can build boards, and that's great and all. But you have to really plan for tomorrow. You have to plan for a year from now, 5 years from now. It's a fun hobby. It's a great hobby. But if you want to do something serious with it, you need to do the work and the planning. There's just no way around it. You just got to take the time. Don't rush it to market. Rushing is a very dangerous thing to do. Just accept the fact that most projects, when given the proper attention and time, testing and everything, you're looking at least a year before you're even close to being ready to release a product to market. That's again why I say that I'm not expecting to be able to put this up for sale on Amazon or Shopify until at least November, December of this year. Just because of the amount of work that's involved and all the testing and stuff I want to do, all the verification, validation, all the test fixtures that we need to do and design and build. Even the enclosure that I want to design with the 3D print and have all ready to go and everything that we want to do. So I appreciate anybody who's stuck with us this far. And again, we're looking at least a year's worth of content, at least, with all the stuff we're going to be doing and all the other stuff that needs to be done. So I'll probably definitely be pulling you guys in for more of the ride. Do less and less off camera when I can. So on that note, I will leave it here. I thank you for checking us out. To my Twitch viewers, I really appreciate you sticking with us and checking us out this long. I hope I'm interesting and the information I'm presenting is interesting. Don't be afraid to research anything I talk about, look into it, fact check me, cross check anything I have to say. I'm always open for constructive criticism. If I'm wrong, I'm wrong. You know, that's the way life is. We don't learn when we're right all the time. We only learn when we make mistakes. So I'm never afraid to be told I was wrong at something. Just be constructive. Be constructive and respectful about it. Don't just, you know, come at me and say, hey, you're wrong. You're an idiot. No, I won't take to that. Just say, hey, look, you know, there's a mistake, and here's where it was. I'm fine with that. Let's do it. Leave in the comments of the YouTube videos, you know, if you find a mistake somewhere. I'll do my best to correct it. Because again, I'm only human. I'm not perfect. And there's a lot that I used to, you know, was involved with ISO and all that, and project management and all that. And it's just, when you don't use it, it kind of rusts, and trying to remember everything. And there's such big processes to deal with. It's just a lot to try to tackle as one person. So just keep that in mind. So I'll get everything updated, make sure all these files are saved, get them pushed over to Git. Again, we'll have the button box files there. You can print, modify, learn, whatever. I'm all good with it. So again, thank you for checking us out. I'll catch you in tomorrow's stream, where I hope we'll be building the first pilot board. Have a good evening.